You know, when you first look at organic chemistry, it can feel like you're just staring at a foreign language. But what if I told you that every single reaction, from the simplest to the most wildly complex, actually follows a predictable blueprint? A set of rules that, once you get them, lets you see the beautiful logic behind how all these molecules are made. Today, we are decoding that blueprint. So let's just get this out of the way. It's the big question that I think haunts so many students. Is this subject just a massive, endless pile of reactions that you have to cram into your brain? Just hoping you remember the right one when the test comes? It's a really common feeling, and honestly, it's a daunting one. Well, the answer is a huge, resounding no. It's not about memorizing hundreds of individual reactions. It's really about learning to read the language of molecules, understanding their structure, their charges, and what motivates them to change. And once you can read that blueprint, you're not just memorizing anymore. You're predicting. All right, so how do we actually start reading this thing? Well, the best way I've found is to think of any organic reaction like it's a short little play. Seriously, it has a beginning, a middle, and an end, and it has specific actors playing very specific roles. This right here lays out the 3 acts of our chemical play. In stage 1, we meet our reactants. You got the substrate, that's the main organic molecule we're focused on, and the attacking reagent, the molecule that really kicks off the action. Stage 2 is the transition. This is a super fast, high-energy moment where a temporary, unstable thing called an intermediate is formed. Think of it as the climax of the play. And finally, stage 3, the result, where we get our final products and maybe some leftover byproducts. So, if the reaction is the play, then what's the script? Well, that's what chemists call the reaction mechanism. And this is the secret choreography. It's the super detailed account of where every single electron moves, which bonds break, which bonds form, and how fast it all happens. It's the step-by-step guide to the whole shebang. Okay, so the first bit of action in pretty much every chemical script is the breaking of a bond, right? Before you can make something new, you have to break something old apart. Chemists have a couple of names for this: bond fission or cleavage. Now, a covalent bond, that shared pair of electrons, it can split into totally different ways. Over on the left, you've got heterolytic cleavage. Think hetero for different. It's an uneven split where one atom gets greedy and takes both electrons for itself. That atom becomes negatively charged, while the other poor atom is left with a positive charge. This is how you get ions. But on the right, we have homolytic cleavage. Homo for same. This is a nice, even, democratic split. Each atom takes one electron, and you end up with neutral but really reactive things called free radicals. And that moment of bond cleavage, that's what creates our main characters for the middle act, the intermediates. Now, these things are incredibly short-lived and super unstable, but their formation is the absolute pivotal event that decides where the rest of the reaction is going to go. This table here introduces our 3 lead actors. You've got the carbocation with its positive charge, the carbanion with its negative charge, and the free radical, which is neutral. Now, while free radicals have their own whole world of fascinating reactions, for our blueprint today, we're going to focus on the 2 charged players. So let's meet them one by one. First up, the carbocation. This is a carbon atom that has lost its share of electrons, leaving it with a positive charge. This creates an empty space, an empty p orbital, which is basically a landing pad for new electrons. It also means the carbon only has 6 electrons, what we call a sextet, when it desperately wants a stable set of 8. This electron deficiency, plus its flat, triangular shape, makes it a perfect target for an attack. But here's the thing, not all carbocations are created equal. The most crucial factor is stability. As you can see on this stability ladder, the more carbon groups you attach to that positive center, the more stable it is. So why is that? Well, those neighboring carbon groups can kind of donate a tiny bit of their electron cloud, helping to spread out and neutralize that positive charge. It's like friends helping to shoulder a burden. And nature always favors the path of least resistance, which means it's going to try to form the most stable intermediate possible. Now, on the complete opposite end of the spectrum, we have the carbanion. This is a carbon that has gained a pair of electrons, giving it a negative charge and a full, happy octet. It has this lone pair of electrons that it's just eager to share or donate. Okay, so we've met the intermediates. Let's talk about the broader roles that our main reactants play. In the most common type of organic reactions, we call them polar reactions. The actors are driven by one really simple motive. Either they're searching for electrons, or they really want to give some away. So these reactions are driven by two main roles. On the left, we've got the nucleophiles. The name literally means nucleus-seeking. These guys are electron-rich. They have a full or partial negative charge, and their whole goal in life is to find an electron-poor spot and donate a pair of electrons. Then on the right, we have electrophiles, or electron-seeking. They are electron-deficient, totally hungry for electrons, and ready to accept a pair. It's basic chemistry, opposites attract. So where does a nucleophile actually attack? It searches for something called an electrophilic center. Take a look at this molecule, chloromethane. Chlorine is super electronegative, which just means it's an electron hog. It pulls the shared electrons away from the carbon. This creates a slight negative charge on the chlorine and, more importantly for us, a slight positive charge on the carbon. That electron-poor carbon is now a perfect target, an electrophilic center, just waiting for a nucleophile to come along. Okay, we've learned all the pieces of the puzzle: how bonds break, the intermediates they form, and the motivations of nucleophiles and electrophiles. So now, let's watch the whole play unfold. Let's read a complete reaction script from start to finish. This is it. The hydroxide ion, OH-, is absolutely loaded with electrons. It's our nucleophile. It spots that electrophilic carbon center in chloromethane, which is our substrate. The blue curved arrow shows the movement. That's the path of the attacking electron pair, moving from the nucleophile to that electrophilic carbon. Now, as that new bond starts to form, the carbon can't have 5 bonds at once, so the weakest one, the carbon-chlorine bond, undergoes fracture. It breaks heterolytically, and the chlorine leaves as a chloride ion. And just like that, we get our final products. Every single step, from the attack to the fracture, is just a logical consequence of how electrons move. And here's the absolute bottom line. This isn't random. It's a predictable dance, and it's all governed by charge and electron flow. If you can identify the electron-rich and electron-poor parts of molecules, you can map out the choreography. You can predict the product. You can read the blueprint. So we want to leave you with this thought. This knowledge isn't just about passing an exam. This is the fundamental toolkit that chemists use every day to build everything from life-saving medicines to advanced new materials. The principles are exactly the same. So now that you have the blueprint, what will you build?